Welcome again to physics class on the topic force between parallel current conductors and talk on rectangular current loop of CBSE class 12 chapter number 4 moving charges and magnetism. Okay, first let's try to learn about forces between parallel current conductors. What do you think when you give two parallel current carrying conductor moving current in the same direction, whether they will attract or repel? So in order to know this, let's try to learn the topic force between parallel current conductors, and later on we will try to learn also about the torque that is experienced on a rectangular current carrying loop when placed inside a magnetic field. Okay, so first let's try to learn about force between two parallel linear conductors carrying current. Now I will explain you first, and then we will go to that part of the description. Okay, now think that there are two parallel current carrying conductors, okay, PQ and XY. Let's take it that current carrying here, say let's take it as I1, okay, and that current moving through the conductor XY, let's take it that the current be denoted by I2 in this XY, and the current that is flowing through PQ, let's denote it by I1. Okay, now then what happen if, say, suppose if there is a current flowing here through this PQ, conductor PQ, then by applying your right hand thumb rule, the magnetic field at this position of the conductor XY, the magnetic field will be denoted by B1, and it will be directed inward, right? Like this. If you try to curl your right hand at the position here, due to this, if you try to curl the current carrying conductor here like this, this through this conductor PQ carrying current I1 passing through this point where there is conductor XY, then your right hand four fingers will curl inward. That direction of the curling of your four fingers of your right hand will give you the magnetic field B1 for this conductor carrying current I1. Okay, so why I call it this as 1B1, because this is due to the current I1 flowing here. Now for the time being, assume that there is no conductor here XY, okay, at this vicinity. That means at this position, what happened, magnetic field due to this PQ carrying current I at this position, that is denoted by B1 vector, and it is directed inward. Okay, now next, if you think it in that way, then what happened, magnetic field, now let's take it that current carrying conductor XY carrying current along the direction XY, okay, this direction XY, okay, I2 is carrying current in this direction. Got it? So this current carrying conductor XY is placed inside the magnetic field B1, which was produced by this current carrying conductor PQ. Okay, now you assume that there is a magnetic field here B1 directed inward perpendicular to the plane of this paper and directed inward. If you assume that XY is lying in the plane of this paper and magnetic field inward, that means your magnetic field B1 will be inward, means your magnetic field B1 will be in the, we may direct it, we may use a symbol as cross like this. So B1 is getting inside. Got it? Perpendicular to the plane and directed inward. So your conductor, okay, conductor XY is placed inside the magnetic field B1, which is directed inward. So your direction of the force F2 will be in this direction by applying your cross product. Okay, why? Because your force F2 will be expressed as what? F2 will be expressed as IL vector cross B vector, right? So your B for this, it will be your B1. Got it? I is what? IL is, this one is I2. And so what happened, if you apply the cross product from this side, IL will be acting along XY here like this. If you try to find out the cross product of IL cross B, the angle between here is 90 degree. Okay, here is 90 degree. So if you do that cross product, naturally by applying your right-handed screw rule or by your right hand curl rule, the direction of the force that will experience by this XY will be directed along this direction. That means toward the conductor PQ. Okay, it will be directed along here like this. Clear? Yes. Similarly, the other conductor, that means this XY, if you think that the magnetic field for this conductor, okay, XY, it will be directed like this in this direction. Got it? Magnetic field, because this is also moving in that direction of this I1. So when you try to find out the right hand curl rule here, what happen if you try to curl your four fingers stretching with your thumb mutually perpendicular to each other, and if you curl it at this point, then what happen, the magnetic field will be coming out. Magnetic field, for which magnetic field? Due to the current I2 flowing through this XY. Got it? So it will be directed outward, perpendicular to the plane of this paper. Got it? Now you have to assume it again, just as we did, that magnetic field is coming outward. Magnetic field, which magnetic field? B2 Y2, because it is produced by the current I2. Okay, so magnetic field produced by this current at this position will be directed outward and perpendicular to the plane of the paper. So what happened, the current carrying conductor PQ carrying current I1 is placed inside the magnetic field B2, and naturally this current carrying conductor PQ will experience a force, okay, by applying the same formula here. So your F1 will be equal to what? IL cross B. If you do that IL cross B, then the direct by your right hand curl rule or by your cross product of vectors, then what happened, the force F1 will be acting along this direction, that means toward the right side. So in this case of F2, which was acting here, it was acting toward the left side, but this one F1 will be acting toward the right side. So F2 and F1 are acting toward each other. So what happened, we can conclude that two linear parallel current carrying conductor carrying current along the same direction will attract each other. Got it? So let's try to see all those descriptions, okay, in the next slide. Now let's see. This is about how to find out the direction of the magnetic field. Okay, so it will be acting toward this when you try to curl it. Okay, acting toward the observer, perpendicular to the plane. Okay, yes. Next is what? Let's try to find out whatever just I have told you. Okay, the descriptions part, I mean. So magnetic field induction at any point on the conductor XY, okay, at this point carrying current I2 due to the magnetic field B1, produced by the linear conductor PQ carrying current I1 is what? B1 is equal to mu naught by 4 pi twice I1 by R. Got it? And this will be directed inward, okay, perpendicular to the plane of the paper and inward. Now the force experience, okay, by this current carrying conductor XY due to the magnetic field B1, okay, is given by F2 mu naught by 4 pi this is B. You know that F2 it will be equal to IL cross B, no? IL vector and B vector are perpendicular to each other, so sine of 90 degree is 1, so we are not putting that value. Okay, so F2 will be equal to what? Twice mu naught by 4 pi times twice I1 I2 by R, where R is nothing but this R is a distance between the two parallel conductor. Okay, this distance is R. Got it? So by doing that formula, by using this formula, the direction of the force F2 will be what? Acting perpendicular to this current carrying conductor XY, and it will be directed toward the other conductor PQ. Got it? Yes. And let's see again, when magnetic field for this conductor XY is under consideration, then magnetic field due to this conductor XY carrying current I2 will be directed outward. Okay, and the expression will be also similar to this. B2 will be equal to mu naught by 4 pi twice I2 by R. Okay, mu naught by 4 pi twice I2 by R. Okay, and so for this again we have to consider that B2, okay, is there coming outward, and inside that magnetic field current carrying conductor PQ is placed. So when current carrying conductor is placed inside the magnetic field, the current carrying conductor will experience a force, and that force is denoted by F1 in this expression. Okay, and so F1 will be equal to what? Mu naught by 4 pi twice I1 I2 by R, and in this case it will be directed toward the other conductor XY. So what happened from these two relations? Okay, this one, it is directed toward PQ, or you can say in our case your F2 was acting toward the left side and your F1 is what? Acting toward the right side. So as they are what? Approaching each other, okay, the two parallel current carrying conductor will attract each other. It is also given here. Okay, you can nicely seen there in the video. If you want to note down, then pause it and you can copy it. Okay, now let's see about if the two parallel current carrying conductor, okay, if they are flowing the current in opposite direction, then what will be the nature of the force? Let's see. Okay, now let's take it that current carrying conductor PQ, as we have said, PQ is having the current flowing toward say upward in this direction. Okay, think that current carrying conductor PQ is lying on the plane of this paper or plane of the screen. Okay, then what happened? I1 is moving in this direction, current I1 I mean. Okay, and the other current XY, we said that from Y to X, okay, the current is flowing in this direction downward. Okay, then the direction of the magnetic field that will be produced here, it will be due to this current carrying conductor, it will be inward. Okay, it will be inward, and the expression of the magnetic field B will be given by what? B2 I mean, B2Y, because it is due to the current I2. Okay, mu naught by 4 pi twice I2 by R. Okay, where R is a distance between the two parallel current carrying conductor. Okay, and it will be directed inward, we have seen, right? Why? Because this is downward, the current direction is downward, and if we try to apply that right hand rule here in this, then what happened? The direction of the force will be what? In this direction, not toward the other conductor XY, rather your PQ, the current carrying conductor PQ, will be directed away from XY. Got it? Why? Because IL is here, B is getting inside. So if you try to curl from the first vector to the second vector, okay, then what happened? You will have the direction of the force in the direction of the thumb. Got it? ILE will be along this direction, okay, along the red arrow, this red arrow represents the direction of the current I1 in that conductor, okay, PQ, and this is directed inward perpendicular to the plane of this paper and getting inward. So your direction of the magnetic field at this point, we can say that it is inward, okay, perpendicular to the plane and inward. So if you try to do the cross product of these IL along here and the magnetic field that is getting inside, then what happened? The direction of the force will be in the direction of the thumb, okay. If you try to curl your four fingers of your right hand, okay, from the first vector I1 to the second vector B2, then the direction of the thumb will give you the direction of this force, okay. Your force F1 can be expressed as what? Yes, your direction of the force can be expressed as what? F1 will be equal to what? I1L cross what? B2. Why B2? B2 is due to the current carrying conductor I2, okay, this one. So what happened when you try to curl your four fingers of your right hand from the first vector to the second vector, then the direction of the thumb will give you the direction of this force, okay. That is what. So let's try to see for the other conductor, okay, that experienced by the other conductor. Now we have to assume that the magnetic field due to this current I1 that will be getting inward, okay, and this will be also getting inward perpendicular to the plane of the screen and getting inward. So what happened when magnetic field is getting inward, current carrying conductor is downward, then what happened? You need to apply that your cross product of this F2. So your F2 will be equal to what? I2L cross B1 vector. Got it? So your IL is flowing here in this direction. I2L will be in this direction. Magnetic field is getting inside, okay, getting inside. So if you try to curl from the first vector to the second vector B inward, then the direction of your right hand thumb will be in this direction, right? So your F2 will be what? Getting away from this current carrying conductor, what? XY, PQ. That means this is P and this side is Q, right? This side is Q, right? So your F2 is getting away from the direction of this PQ, right? Yes. Let me remove it like this and let's try to see for the second for this one, okay. And then what happened? Your magnetic field B1 is expressed as what? Mu naught by 4 pi twice I1 by R directed inward, as I have said. So this red magnetic field shown with a red arrow, this is a magnetic field due to this current carrying conductor I1 shown with the red color, okay. Now the force experienced by this conductor shown in the black color, that will be given by what? F1 will be equal to what? Mu naught by 4 pi twice I1 by I2 by R, okay. This is nothing but it is just like IL cross B, okay. And IL is what? Your IL will be I2 times L. B is what? This portion is B. Got it? This B, okay. Clear? So and it will be directed toward the right side. See, it is directed toward the right side, okay. So as the two current carrying conductor, okay, experience forces which are away from each other, got it, then what happened? We can conclude that those parallel current carrying conductor carrying current in the opposite direction will repel each other, okay, right. So let's try to define 1 ampere or definition of an ampere we can see. Now if you take it that okay, these two parallel current carrying conductor just like this, or along the same direction, whichever you like it, you can take it, okay. And if you take it that if this current flowing here is taken as 1 ampere, okay, here also 1 ampere, got it, and the distance between them is also made as 1 meter, got it, then the force experience, as we have just seen, that force, this is not actually the force, rather the force per unit length we have to say, okay, force per unit length, that will be equal to what, mu naught by 4 pi twice I1 I2 by R. When we say here also IL cross B, no, that IL cross B, so I is this one, right, and your B is this one. So what happened, I and B, we need to multiply it, got it, so that IL, if you bring this side, that L, then this F1 is nothing but F1 and F2 are nothing but this is a force experienced by those respective conductor per unit length of that particular conductor, okay. So we can say force per unit length, got it, this is also same as like that. So force per unit length experienced by either of the conductor will be equal to mu naught by 4 pi twice I1 I2 by R, got it. Now if we met that condition, that the current flowing through the parallel conductors be met as 1 ampere and the distance between them is also 1 meter, and if they are placed in vacuum, okay, if these two are placed in vacuum, then the force experienced by them will be equal to what, 2 into 10 to the power minus 7 Newton per meter. Then we can define simply that 1 ampere as that amount of current, okay, which when flowing through each of these two parallel conductors placed in vacuum at a distance of 1 meter apart, attract or repel each other with a force of 2 into 10 to the power minus 7 Newton per meter of their length. This of their length is very much required because this force is force per unit length of their conductor, okay, of that conductor. Next, we will try to do this talk on current rectangular loop when placed inside the uniform magnetic field. Let's see it, okay.
A current carrying conductor placed in a uniform magnetic field experiences some force. The magnitude of this force is determined by using the formula F is equal to BIL sin theta, where theta is the angle between the direction of the magnetic field and the direction of current. The direction of the force acting on the conductor can be determined by using Fleming's left-hand rule. According to the rule, when we stretch the thumb, the index finger and the middle finger on the left hand in three mutually perpendicular directions, if the middle finger indicates the direction of current in the conductor, the index finger indicates the direction of the uniform external magnetic field. Then, the thumb indicates the direction of the force on the conductor. Now, let us discuss the forces acting on a rectangular current carrying loop when it is placed in a uniform magnetic field. Consider a rectangular loop PQRS of length L and breadth B placed in a uniform magnetic field in such a way that the plane of the loop is parallel to the magnetic field. Connect the rectangular loop to a battery as shown, such that the current in the loop is along the direction PQRS. Let B be the magnetic induction of the uniform magnetic field between the two magnets, and I be the constant current passing through the rectangular loop. To simplify the understanding of the topic, we neglect the ends of the loop from where the current enters and leaves the loop. The magnetic field exerts some force on the arms of the current-carrying rectangular loop. The direction of current in the arm PQ of the loop is perpendicular to the direction of magnetic field. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm PQ of the rectangular loop due to the magnetic induction B is F1 is equal to BIL sin 90 which is equal to BIL, where L is the length of the arm PQ. Let this be equation 1. Here, the direction of the force is determined by using Fleming's left-hand rule. Stretch the 3 fingers of left hand in 3 mutually perpendicular directions. Here, the direction of the magnetic field is from north to south, represented by the index finger of the left hand. The direction of current is from P to Q of the rectangular loop, represented by middle finger, and the direction of thumb represents the direction of force acting on the arm PQ of the loop. That is, the force is acting downward with respect to the plane of the loop. The direction of the current in the arm QR is parallel to the direction of the external magnetic field. This implies that the angle between the direction of the current in QR and the direction of the magnetic field is 0 degrees. Sin 0 is equal to 0. Hence, the magnitude of the force acting on the arm QR of the rectangular loop due to the magnetic induction B is F2 is equal to 0. Let this be equation 2. The angle between the direction of the current in RS part of the loop and the direction of the magnetic field is 90 degrees. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm RS of the rectangular loop due to the magnetic induction B is F3 is equal to BIL. Let this be equation 3. Here, using Fleming's left-hand rule, we find that the force acts upwards with respect to the plane of the loop. The angle between the direction of current passing through the arm SP of the loop and the direction of the magnetic field is 180 degrees. Sin 180 degrees is equal to 0. Hence, the magnitude of the force acting on the arm SP of the rectangular loop due to the magnetic induction B is F4 is equal to 0. Let this be equation 4. We observe from the equations that the magnitudes of F1 and F3 are equal. As they act on the loop in opposite directions, they are unlike forces. Hence, the net force acting on the body is 0. As the two forces F1 and F3 are non-collinear and are separated by the perpendicular distance B, which is equal to the breadth of the rectangular loop, they result in turning the loop. These two forces cause the rectangular loop to rotate about an axis that lies in the plane of the loop, parallel to its length and passing through its center. Thus, the axis of rotation of the loop passes through the midpoints of QR and SP. The magnitude of the torque τ1 due to F1 is equal to the product of F1 and the perpendicular distance between the point of application of F1 and the axis of rotation. This gives τ1 is equal to F1 into half of B. Similarly, the magnitude of torque τ3 due to F3 is equal to F3 into half of B. The net torque on the loop τ is equal to the sum of τ1 and τ3, which is equal to F1 into B by 2 plus F3 into B by 2. But F1 is equal to F3 and both are equal to BIL. Then, τ is equal to BIL into B by 2 plus BIL into B by 2, which is equal to BI into LB. As L into B is equal to the area of the rectangular loop A, we can denote the torque acting on the rectangular current loop τ is equal to BIA. The net torque on the loop tends to rotate it in the anti-clockwise direction when viewed from SP side of the loop. We know that torque is a vector. Hence, the expression for torque on the rectangular current carrying loop placed in the external magnetic field can be represented using vectors. We know that magnetic induction B is a vector. We now assume another vector A called the area vector. The direction of the area vector is given by right-hand rule. If the right hand is stretched and the four fingers of the hand curl in the direction of the current in the loop, then the thumb, which is extended out, indicates the direction of the area vector. Hence, the direction of the area vector in this case points into the loop when we observe it from top, such that the current in the loop is in the clockwise direction. If theta is the angle between the two vectors, then the torque on the loop is given by the cross product IA cross B, whose magnitude is equal to IAB sin theta. We now define a new vector, magnetic moment, denoted by M, which is equal to the product of I and A. Thus, the direction of M is the same as that of the area vector, and its SI unit is ampere meter square. Hence, torque on the current-carrying rectangular loop is given by the expression τ is equal to M cross B, and hence, the magnitude of the torque on the loop is given by MB sin theta. In this case, the angle between the magnetic moment and the magnetic induction is 90 degrees. As sin 90 is equal to 1, the torque on the loop is the maximum. Now let us consider another case where the magnetic moment makes an angle theta, other than 90 degrees, with the direction of the magnetic field. That is, the angle between the directions of the area vector and the magnetic field is other than 90 degrees. When the current passes through the rectangular loop, the magnetic field exerts some force on the sides of the rectangular loop as discussed earlier. Here too, the angle between the direction of current through PQ and the direction of magnetic field is 90 degrees. Hence, the force acting on the arm PQ of the rectangular loop due to the magnetic induction B is F1' is equal to BIL. Let this be equation 5. Here, using Fleming's left-hand rule, we find that the force acts downwards in a direction perpendicular to the plane containing B and I. In the case of arm QR, the length of the arm QR is not perpendicular to the direction of the magnetic field. Area vector makes an angle theta with the magnetic field. Hence, the angle between the magnetic field and the current through QR is 90 minus theta. Then, the force on QR, part of the loop due to the magnetic field, is F2' is equal to BIB sin 90 minus theta, which is equal to BIB cos theta. Let this be equation 6. The direction of force F2' is obtained by using the right-hand rule. When the four fingers of a stretched right hand curl from the direction of current in QR towards the direction of magnetic induction B, the thumb indicates the direction of the force on QR. Thus, the force F2' acts perpendicular to the plane containing I and B, outward of the loop along its axis of rotation. The direction of current through the arm RS of the loop is perpendicular to the direction of magnetic field. Then, the force acting on the arm RS of the rectangular loop due to the magnetic induction B is F3' is equal to BIL. Let this be equation 7. Using Fleming's left-hand rule, we find that the force acts upward in a direction perpendicular to the plane containing current and magnetic field. the direction of current through the arm SP of the loop makes an angle 90 minus theta with the direction of the magnetic field. Then, the force acting on the SP due to the magnetic field B is F4' is equal to BIB sin 90 minus theta, which is equal to BIB cos theta. Let this be equation 8. The direction of force F4' is obtained by using right-hand rule. When the four fingers of a stretched right hand curl from the direction of current in SP towards the direction of magnetic induction B, the thumb indicates the direction of the force on SP. Thus, the force F4' acts perpendicular to the plane containing I and B outward of the loop along its axis of rotation. We observe that the forces F2' and F4', which are equal in magnitude, act along the same line, that is, along the axis of rotation. Hence, they are collinear. But they are unlike as they act in directions opposite to each other. Hence, these two forces cancel each other and their resultant is zero. Thus, these two forces do not constitute torque. On the other hand, the forces F1' and F3', which are equal in magnitude, act in opposite directions to each other and are not collinear. Therefore, the resultant of these two forces constitutes torque on the loop. The net torque acting on the loop tends to rotate it in the anti-clockwise direction when viewed from PS. The magnitude of torque due to F1' is equal to the product of force and perpendicular distance between F1' and the axis of rotation of the loop. Let D be the perpendicular distance between the force F1' and the axis of rotation of the loop. As the angle between the area vector and the magnetic field is theta, from the geometry of the figure, the perpendicular distance D between the force F1' and the axis is equal to B by 2 into cos 90 minus theta, which is equal to B by 2 into sin theta. Thus, the torque T1' on the loop due to F1' is equal to F1' B by 2 sin theta. Similarly, the torque T3' on the loop due to the force F3' is given by T3' is equal to F3' B by 2 sin theta. Hence, the net torque T' on the loop is given by the sum of T1' and T3'. This is equal to F1' B by 2 into sin theta plus F3' B by 2 into sin theta. But F1' is equal to F3', and both are equal to BIL. Then, T' is equal to BIL B by 2 into sin theta plus BIL B by 2 into sin theta. Replacing L into B with area of the loop A, the torque on the loop T' is equal to BIA sin theta. So far, we have learnt about the torque on a current-carrying rectangular loop placed in an external uniform magnetic field, in the case where the area vector makes an angle other than 90 degrees with the direction of the magnetic field. On rotation of the loop about its axis, due to the torque on it, if the angle theta tends to 0, perpendicular distance between the forces tends to 0, and this results in 0 torque on the loop. Also, while the angle reduces to 0, the value of sin theta becomes 0 which results in zero torque on the loop.